Good morning, students. Yesterday we discussed about different types of unit cells. Those unit cells are cubic unit cell, then tetrahedral unit cell, orthorhombic, unit cell, then hexagonal, rhombohedral, and or which is also called trigonal, then monoclinic and triclinic. Are you clear? So there are 7 types of unit cell. Those are cubic unit cell, tetrahedral unit cell, orthorhombic unit cell, hexagonal unit cell, rhombic or trigonal unit cell, monoclinic unit cell, and triclinic unit cell. See, all these unit cells having parameters. Those are edge lengths ABC and axial angles. Those are alpha, beta, gamma. Are you clear? See, all the structures and how they are related, how to differentiate these, everything clearly we discussed yesterday. And we can find the possible variations also. Take for example orthorhombic unit cell. The possible variations in orthorhombic unit cell is primitive, body center, face center, and end center unit cell. Are you clear? So these are variations, and among all these 7 we can find 14 variations, and those variations are called Bravais letters. Are you clear? Okay, so detailed diagram and how to compare it you will get in notes. You have to go through, just see the sides, edge lengths, and you can easily confirm about the unit cell. So a particular unit cell which consists ABC as edge lengths and alpha beta as angles. This is nothing but an axial angle. Okay, dear students, today we shall discuss about the calculation of number of particles for the atoms present in primitive unit cell, body centered unit cell, and face centered unit cell. Are you clear? So calculation of particle you will get for 2 marks. Calculation of particles present in primitive unit cell, body centered unit cell, and face centered unit cell. We shall discuss. Okay? Now, number of particles presenting. Number of particles presenting. See, number of particles presenting primitive unit cell. In primitive unit cell. You know a primitive unit cell which is nothing but a simple unit cell, unit cell. Just we can join here, and this is nothing but a simple cubic unit cell. Are you clear? See, yesterday we already discussed this, and among these, see here, these are nothing but the points which is nothing but the lattice side, and how to calculate number of particles in a primitive unit cell. See, in primitive unit cell, the particles are present only at the corners. That you have to remember. How many corners are there? 8 corners. We can easily then we can see this heading a type of unit cell, where we can find, see, any face you can see. How many corners? 1, 2, 3, 4. Another back side. How many corners are there? 8 corners. Just to identify and understand it, we have to understand. Then we can easily write. No need of biotic this. How to calculate number of particles in primitive unit cell, body centered unit cell, and face centered unit cell. See, as it is nothing but a face, and you have to see 8 corners, 4 corners, and back side. Are you clear? So you can observe here also 1, 2, 3, 4, 5, 6, 7, 8. How many corners are there? 8 corners. Okay, in primitive unit cell, particles are present only at the corner. Very slowly I am going to deliver. Particles are present only at the corner. So how many corners are there? See, 8 corners, 8 corners, 8 corners, and see, each corner is contributed by. See, in an atom, you take for example this, you can join another one like this. So we don't have more. This also you can join it. Like that. It continues. Another you have to join. So contribution at this point is only 1 by 8, which is nothing but a small part which I can show in the diagram. You can see here in diagram. You can see the contribution to each point is only this much. Are you clear? So this is nothing but the contribution. How much? It is nothing but 1 by 8. 1 by contribution at the corner is only 1 by 8 part. See, actually, in order to get a sphere like this, only 1 by 8 part is contributed at the corner. How much? 1 by 8 part is contributed like this. Can you see the diagram? Suppose, consider it is an atom. This is the number of one atom. Now, this sphere in 8 corners, contribution is 1 by 8 per unit cell. Are you clear? So, it is nothing but into 1 by 8 particles per unit cell. It is its contribution. So therefore, 8 into 1 by 8. So you will get 1 particle or 1 atom. Are you clear? What the number of atoms present in or particle present in primitive unit cell? It is nothing but 1 atom. How? See, you can see by the diagram. You can easily remember. You can easily calculate. Are you clear? So it is nothing but the contribution. Contribution at a corner is only the small part. How much it is? 1 by 8. Why we have to take 1 by 8? It is nothing but the contribution in the corner. See, imagine an atom is a spherical, a sphere, a hot sphere. And in primitive unit cell, see other units are binded each other. Like this, you can see any box like this, you can see these boxes. So you have to place one above the other. They don't have both boxes. Again this side, again this side, again this side. These are nothing but the contribution. At that time, how it contributed, that is nothing but the 1 by 8. 1 by 8. That is nothing but a primitive unit cell. Are you clear? It is nothing but a primitive unit cell. In a primitive unit cell, contribution towards the corner is only 1 by 8 per atom. So therefore, per unit cell, 8 into 1 by 8 is equal to 1 atom or particle. You can easily write. Are you clear? So you have to calculate the number of particle or the atoms present in primitive unit cell or simple unit cell. Are you clear? So how many particle it is? It is nothing but one atom. The total number of atoms present in primitive unit cell is only 1. 8 into 1 by 8 is equal to 1. You may get one more question. The total number of particles present in primitive unit cell or simple unit cell, how much you have to? It is nothing but 4. So then again, we shall go for the total number of atoms in body center units. In body center units. In body center units. So what do you mean by a body centered unit cell? A body centered unit cell is defined as the particles present in center of the body and including the corner particle is called body centered cubic unit cell. Are you clear? In body centered cubic unit cell, see, in body centered cubic unit cell, one of the particle is at the center of the body. It is nothing but, so this is nothing but one of the particle which is present at center of the body. And what is the definition? Body center is nothing but one of the particle at the center of the body and corner particles. What is the total number of corner particles contribution? It is nothing but 8 into 1 by 8. In body center, simple, and also in face center. So therefore, the total number of particles in BCC, body center, is 1 at the body according to its definition. And see, 8 particles and its contribution is 8. This is nothing but the corner particles. And therefore, you will get 1 plus 1. So you will get, what is the total number of atoms or the particles present in BCC or body center is 2. Are you clear? Understood? How many particles are there? How many atoms are there in BCC? Only 2. One is from the center of body and another one is contribution towards the corners. So therefore, 1 plus then 8 into 1 by 8 we will get 1. So it is nothing but 2. The total number of particles present in body center cube is what? 2. Are you clear? Okay. Then we shall go for total number of particles present in face centered cube. In face centered cube. See, in face centered cubic lattice, see, you can see the faces. You can see, just to see this. It is nothing but a cube. See, this face is opposite to back side. Another one. And this side. See, we can find the 6 phases 1, 2, and 3. How many? See, contribution for each phase is 1 by 2. As if this is also phase and this is also phase. How many phases? 6 phases. Contribution to each phase is what? 1 by 2. 1 by 2. And what do you mean by phase center cube? It is nothing but the particles present at phases and including corner particle. So that is nothing but a phase center cube. Total number of particles present in FCC phase center is, say, observe the diagram here, see the diagram. So this is nothing but one contribution phase, and this is another one, and this see one from this another. So you can find 1, 2, 3, 4, 5, 6 phases, and contribution towards each phase is 1 by 2, 1 by 2. Now we can easily calculate. Try to understand FCC. Are you clear? Now it is nothing but in FCC. In FCC, we shall discuss. In FCC, phase center cube. Are you clear? In phase center cube. In phase center cube. Again, see the diagram. So here, and this is nothing but adjacent. Quite opposite. And here is one from, you can see the box here. See, one, another. Contribution in each phase is 1 by 2. Contribution. So you can easily observe in the diagram. You can see the diagram. We can judge it. Are you clear? See, this is nothing but another one. And this is nothing but the total number of particles in FCC. We shall calculate. See, one is corner particles, and according to phase, 6 phases into 1 by 2 particle per phases. Then plus the particles present at the corner, same thing, 8 into 1 by 8. So is equal to 3 plus 1. So you will get 4. The total number of particles present in FCC is 4. How it is? Say 6 into 1 by 2, you will get 3 and 1 particle from the corner. So totally, we will get how much? See, 4 atoms are there. Total number of atoms or particles present in phase centered cubic unit cell is how much? 4. Are you clear? So dear students, you understood about the calculation of number of particles present in simple or primitive unit cell, body centered unit cell, and phase centered unit cell. Are you clear? See, in phase centered unit cell, you must know what is phase centered, what is body centered, what is primitive or simple unit cell. In phase centered, the particles are present other than corner. So where they are present on the phases, contribution towards each phase is 1 by 2. How many phases are there? 6 phases. So therefore, the total number of particles is what? From phase 3 and 1 from corner. You know the corner particles. The contribution is 1 by 8 particles. So therefore, the total number of particles present in phase center is 4. Are you clear? And we can see the diagram. Very easily you can understand. See this one and this two. And this is another. Are you clear? So definitely you will get 1 2 marks question. Calculate the total number of particles present in FCC or total number of particles present in BCC or the total number of particles present in simple cube. Are you clear? Understood? Okay. So that is nothing but total number of particles in FCC, BCC, and as well as simple itself or primitive itself. Okay, we shall continue our discussion on as in a solid state. What is the space we can find? There is no space, very small space. As all the particles, assume all the particles are in spherical shape, they are in a hard sphere, they arrange in a well order, and it gives different types of geometries and different unit cells was what we studied. Now, how they are packed each other, how they are packed each other, and that is called packing efficiency. It's called packing efficiency. What do you mean by packing efficiency? The number of space occupied by the particle. Are you clear? See, it is nothing but the space occupied by the spheres. That is nothing but the packing efficiency. We shall study how these particles arrange. We shall study one by one. Now, see, this is nothing but, we will call this as a sphere. We will call this as, so this is nothing but arrangement of particles. We are assuming the particles in a spheres. See, in these closed spheres, you can easily consider this particle. See, I consider this the center particle. What are its nearest neighbors? Its nearest neighbors are this one and this. So I can show by color chart. See, this one is its nearer and this is another. And this is called coordination number. You have to remember another concept. Define coordination number in a, see, coordination number. Coordination number. So what do you mean by coordination number? The number of nearest particle, of a particle is called coordination number. So this is nothing but one dimensional arrangement. Only one row you can find. And here, what is the coordination number? Coordination number in one dimension is only 2. So this is 1 and this is another. What do you mean by coordination number? The nearest neighbors of a particle. The nearest neighbors of a particle is called what? Coordination number. In one dimensional arrangement, what is the coordination number? Coordination number is 2. If we consider the center sphere according to the diagram, the considered sphere attaches 2 other nearest neighbors. That is called coordination number. Very simple. You will get one more question. Define coordination number. It is nothing but the number of nearest particle. Are you clear? What is the coordination number in one dimension? In one dimension, coordination number is 2. So we shall study in 2 dimensions. So this is one dimension. Say I am going to draw the spheres. You can easily observe here. Just see the diagram. See, in the second layer, I am going to place the spheres exactly below it. Can you see? See, second layer is placed exactly below the first layer. I am going to place another thing. third layer is also placed exactly below the second layer. Are you clear? See, it is nothing but a two-dimensional arrangement. See, it can also be, you can see another diagram. See, here you can see. This is one of the sphere, another one. See, as 4 to 5 spheres are arranged, and in this arrangement, the second layer is placed in the depression of the first layer. Here, the second layer is placed exactly below the first layer, and here, the second layer is placed in the depressions of the first layer. In the depressions of the first layer. Are you clear? See, again, in the depressions, you can extend. So, like this is nothing but an arrangement. Where again it is placed in the depressions. So you can see, we can form what type of geometry it can exist. Say, while drawing one of the spheres, these are nothing but the arrangements. Okay, in two-dimensional arrangement. In two-dimensional arrangement. See, now I am going to take the coordination number of this sphere. What is the coordination number? See, this sphere is attached. You can see this one. It is not touched here. 2, then it can 3 and 4. Are you clear? And what type of geometry it can exhibit? See, I am going to join these points. See, it exhibit. See, I am going to join by a straight line. These points is joined by a straight line. So it is nothing but a square plane. A cubic close line is not. Are you clear? It is nothing but a square. Therefore, in a two dimension, when spheres are placed exactly one below the other, the geometry of it is square. Are you clear? Understood? You will find very clear. What is the coordination number? Its coordination number is, so this sphere is joined to 1, 2, 3, 4. Its coordination number is 4. Very easily you can understand. Shall I go the second arrangement? So two-dimensional arrangement can be possible in two ways. One is the spheres are placed exactly one below the other. We'll also call as a type packing. And in this packing, the second layer is placed in the depressions of the first layer. In the depressions, we can observe here. See, this is one layer and this is the second layer. What is the coordination number and what are the geometries exhibited now? So I am going to consider this particle at this point. Okay. If it touches, we can see here 1, 2, 3, 4, 5, 6. It can easily touch these 6 spheres. See, again I am going to shade this. Be particular about the diagram, easily you can understand this. See, now I am going to draw this geometry. Shall I join? 1, 2, 3, 4, 5, 6. We will get a hexagon. What is the coordination number? See, coordination number is number of nearest particle. So this particle touches to 1, 2, 3, 4, 5, 6. Its coordination number is six. What is the geometry here? Geometry is nothing but a hexagonal. So it is called hexagonal close packing, HCP, hexagonal close packing. And it is called cubic close packing. Okay, very easily you can find the hexagon. Be particular about the diagram, you can easily understand. See, as these particles, what is the arrangement in these two dimensions? The spheres are placed in the depressions of the first layer. Second layer spheres are present at the depressions of the first layer. Then we will get a hexagonal cubic packing, close packing. Hexagonal close packing. What is the coordination number? Coordination number is 6, which is called hexagonal close packing. If you go for this diagram, clearly you understood? See, these spheres, one layer, another second layer is placed exactly below the first layer. Exactly below the first layer. And what is the coordination number? Its coordination number is, see, 1, 2, 3, 4. Coordination number is 4. What is the geometry? It is nothing but a square. You can find the square. Are you clear? So, in two dimensions, two possible geometries will, and coordination number is when the spheres are placed one below the other, then its coordination number is 4 and the geometry of it is square. If you go for when the second layer is placed in the depressions of the first layer, then the geometry obtained is hexagonal close packing. And hexagonal close packing. What is the coordination number? Coordination number is 6. Are you clear? So that is nothing but two-dimensional arrangement. As you can see, these spheres, when these spheres are arranged in depressions one below the other, see, one below the other, in the depressions of the first layer, you can see, we can find the small spaces between them. You can see some of the space which observed, and these are called voids. These are called voids. These are holes. A small particular hole is present, which we will call as voids. See, these voids, which even though we are telling the solids are strong, there is no gap, even though it has certain holes, spaces between those arranged spheres, and it gives efficient in packing. So all solids are deficient, and here these voids are classified into two types. See, those are classified into two types. One is tetrahedral void, another one is octahedral void. So you can see some of the spheres which I brought here. Just you can see the spheres. When these spheres are placed, so this as I placed one dimension, what is the coordination number here? Coordination number of this particle is 1 and this one. That's all 2. You can easily observe. As you place the other particles in the depressions of this, see, this is nothing but the area in the depressions. You can find the small gap. I think you can observe the gap. See, which are called. See, these, when these are arranged, we will find the gap, and that gap is called void. Are you clear? And these voids, imagine it's an ionic solid. The anions, which is bigger in size, are arranged like this, and cations which occupies the space. And it has a particular geometry. When this is covered, which is nothing but a tetrahedral void and octahedral void. So this is nothing but how to understand a tetrahedral void. See here three spheres. If one sphere is placed here, you can find a tetrahedral void, which is nothing but a tetrahedral void. You can see it is nothing but a tetrahedral void. As three spheres and one sphere is placed above and it generates a void, that void is called tetrahedral. Are you clear? See, you can easily find it. So here one sphere is placed and you can find the void, and this void is tetrahedral void. What is the geometry of that void is nothing but a tetrahedral. Easily you can understand. See, and again octahedral void. Octahedral voids are obtained by six spheres. See, shall I draw here? 1, 2, 3, and other. See, 1, 2, and 3. And this void is nothing but octahedral void. Octahedral void. Are you clear? See, octahedral void is obtained by six spheres. And this is nothing but a tetrahedral void, which is obtained by 3 and another 4. You can observe in the diagram in spheres. So, we will find two types of voids. One is tetrahedral void, another one is octahedral void. Among these, how to differentiate? You can also find in this diagram. If you place the other spheres like this, we can observe the tetrahedral as well as octahedral void. See, these diagrams are there in your textbook. So these are nothing but a tetrahedral void. See, all these are tetrahedral void. You can find an octahedral void as the spheres are placed. See, this series of voids gives a deficiency in the crystal. It has certain space. So during crystallization, some of the impurities or the arrangement of particles, even though solids are hard, and this is the real arrangement in a solid. Are you clear? So some of the diagrams in the packing, we shall study tomorrow. I will show you. But you have to remember what is a hexagonal close packing and what is a square close packing. And when in one dimension, what is the coordination number? In one dimension, coordination number is 2. In two dimension, there is two types of is possible. Two types. One is square plane and one is hexagonal close packing. When the spheres are placed in the depressions of second layer, spheres are present in the depressions of the first layer. Then we study about the voids. We can find the tetrahedral void as well as octahedral. In any geometry, in any unit cell, the number of octahedral void is equal to n, and number of tetrahedral void is equal to n in number. But what about tetrahedral void? Tetrahedral void is equal to 2 into n. See, suppose octahedral voids are 1 in any unit cell, you can find in the tetrahedral that is nothing but 2. If suppose a geometry shows octahedral void as a 10, what about tetrahedral void? Tetrahedral void is 20. Are you clear? So this is nothing but the arrangement of spheres, and we will assume all solids have the circular shape or sphere, and the arrangement in two dimension. Again, we will find two type of geometry. One is square, another one is hexagon. And again we studied about the void, which is nothing but a tetrahedral void and octahedral void. Tetrahedral void is obtained by 4 spheres. I'll show again. See, this is nothing but a tetrahedral void. It is nothing but a tetrahedral void. So you can find a tetrahedral void easily. See, this place is covered by either it may be a smaller ion which is nothing but a cation, and bigger size ion is nothing but an anion if you compare in a ionic solid. Okay, we shall stop our discussion here. Today we discussed about only to calculate the number of particles in primitive unit cell, body centered unit cell and face centered unit cell. And then next we studied about the coordination number and packing efficiency. The number of space filled by the particle, which is nothing but a packing. General name is nothing but a packing. Here, in one dimension, what is the coordination number? 2. In 2 dimension, what is the coordination number? 4. And again 6. When the spheres are placed, one below the other will get square kind of limit. And when the spheres are placed, in the second layer is placed in the depressions of the first layer, we will get hexagonal close packing. Repeatedly, I had told you, you can easily understand. In entire solid state topic, this concept, if you understood by the diagram, then only you can remember. All the students our experience is, all the students are telling about the arrangement, the packing, it is difficult. Just see the diagram. See, calmly you observe, you can draw it. What is coordination number? Nearest neighbors of a particle is nothing but a coordination number. That means one of the atom, how much it touches to other, that's all. Nothing more. Are you clear? Okay, some of you may get bored. Now, slowly I am going to deliver the syllabus. Only this, then other part is very simple. Try to understand how this arrangement, what is coordination number, what is one dimension arrangement and second 2-dimensional arrangement. In the 2 dimensions we have 2 types. One is second layer is placed exactly the first layer, and second layer is placed in the depressions of the first layer. Okay, so today I am going to conclude my class. Even though Sunday only nearly 40 to 50 students are watching the live class, I think due to net problem, you may download it afterwards and you can observe. Thing is, every day you have to read. Whatever the portions we have completed, write down the notes clearly and be in touch with your syllabus. Okay, thank you.